Here we have a situation where the initial angular velocity of a rotating beam is 2 revolutions per second, about 1,001, about like 2 revolutions, I'm sorry, not radians, 2 revolutions per second. Well, that'd be a little fast. Okay? And it goes through 14 revolutions in 3 seconds. Now I ask you to analyze this situation using a graph. Well, most of you drew a graph that looks something like this without all the labeling. But it's understood that omega is in this direction, t is in this direction. We don't need an omega axis. We just need an interval of the t-axis, a 3-second interval, and we can sketch this situation. Now we sketch it with a positive slope. How do we know the slope is positive? And we are given that the acceleration is uniform. So which of course is saying that omega versus t is linear, since alpha is the rate of change of omega with respect to t. And make sure you understand exactly what I said and what it means. Okay, well, how do we know this is going to be a positive slope? Okay, well, we know that because if there was no angular acceleration, it would continue moving at 2 revolutions per second for 3 seconds. It would all go through 6 revolutions. That's very obvious, something you should probably immediately think of. So you know that since it goes through 14 revolutions, it has to be speeding up. That's going to give you a positive slope on your omega versus t graph. So what other details do we know? We don't know omega f. That's a question mark at this point. Okay, somebody brought up that the area would be the integral of the function, and that's absolutely true. Area represents the displacement, the angular displacement, the delta theta. So our area would be 14 revolutions, and that would be the integral of our omega versus t function over this 3-second interval, the definite integral over this 3-second interval. Did I say that right? Interval. The definite integral over the 3-second interval. I think I said it right, but I want to be careful. Okay, the integral, of course, we understand to be the average value times the length of the interval. So from this, knowing that the area is a displacement, the area is the integral, we know that the integral of the omega versus t function is 14 revolutions. Knowing that the integral is the average value times the length of the interval, well, the length of the interval is 3 seconds, we immediately conclude that the average angular velocity is 14 revolutions divided by 3 seconds, or 14/3 revolution per second. Now, we didn't have to go through all this reasoning, but we did, because I let the class chime in. It's very simple that the average velocity, by the definition of angular velocity, the average angular velocity is the change in angular position over the change in time, completely consistent with the meaning of the integral. And since we have a constant slope, we can just divide the change in velocity by the time interval, and we get the average angular velocity. So we could have just used the fact that omega bar is the average rate of change of angular position with respect to time. Straight line graph tells us that omega bar is constant, so right there is our average angular velocity. Now you got to digest all this. This is really important. You got to understand this at this level, not just at the level of equations, but at the level of a deeper understanding of motion. Well, how does that help us with the graph? Well, we know from what we did in the first week of class that the average value of a linear function over some interval is the average of its initial and final values. Also, that the average value occurs at the midpoint of the interval. It would be represented, the point representing the average value of the angular velocity at the midpoint time is going to occur at the midpoint of this segment. And that tells us geometrically, just using just simple geometry, that this triangle is geometrically similar to this triangle. This is the halfway point, so the two runs are equal, and the two rises have to be equal because the slope of this line doesn't change. Both of the runs are horizontal. This angle is the same as this angle, this side's the same as this side. These are right angles. You can reason that out in many ways. Okay, well, what's the rise here? Well, the rise is from 2 revolutions per second to 14/3 revolution per second. So the rise here, man, let me kind of do a little demarcation. That's the rise. 14/3 revolution per second minus 2 revolutions per second. And of course, this side being equal, this rise being equal to this rise, that's also the rise here. So the total rise from here to here is the total change in angular velocity. Total change in omega, got a bad spot on that chalk, let me reverse it. Total change in omega is what? 2 times 14/3 revolutions per second minus 2 revolutions per second. Okay, well, 2 is 6/3. 14/3 minus 6/3 is 8/3. 2 times 8/3 is 16/3 revolution per second. And that's your delta omega. Now, there are many other ways that could be reasoned out geometrically from the given information. This one is actually fairly straightforward because there's a simple picture that goes with it. Then we just have to do the arithmetic. Subtract this omega from this one. That's half the change from here to here, so we double that change. Okay, so then your angular acceleration is delta omega over delta t, which is your 16/3 rev per second, divided by your 3 seconds, which is 16/9 revolutions per second squared. That really is a bad piece of chalk. I have to throw that away. Okay. Now we have to be able to do this kind of reasoning because it's really easy to visualize, and the alternative is to either quote equations that we might not be completely sure of, or set this up as a differential equation with a quadratic position function and a linear velocity function. Now, you should be able to do either of those other two things, but you want to be able to do this as well. And let me note one other thing. Somebody said that once we get the average angular velocity, we double it and we get the final angular velocity. We only double the average angular velocity to get the final angular velocity if the initial angular velocity is 0. Okay? Otherwise, we can double the difference between the initial and the average and add that to the initial, which is what we could do here if we wanted to find the final. And we never did find the final, but if we added the 16/3 revolution per second change to the 2 revolution per second initial, we'd get 22/3 revolution per second. That would be the final. Okay, well, we can do all that. But we have to understand the conditions under which we double the initial angular velocity. And that depends on the initial angular velocity. Did I say double the initial? Double the average angular velocity. That depends on the initial angular velocity being 0. When you have a shortcut like that, you can't let yourself forget the circumstances under which it holds. So we have this. Under the conditions of uniform angular acceleration. If angular acceleration is not uniform, we could make this happen even if this isn't zero. But you'd have to have a special kind of function. Okay, this, you need to be able to reason things out, both verbally, graphically, and analytically, either through the equations of uniformly accelerated motion, if motion happens to be uniformly accelerated, or through a differential equation with initial or final or boundary conditions.